The last method for apportionment that we are going to discuss is the Huntington-Hill method. This is the method that is currently used to apportion congressional representatives. It was originally developed around 1911 by Joseph A. Hill, who at the time was the chief statistician of the Bureau of the Census. It was then refined by Edward V. Huntington, who is a math and mechanics professor at Harvard. Because of all the drama with apportionment, Congress established a panel of mathematicians and asked them to investigate the mathematics of apportionment back in 1929. And they decided that they liked the Huntington-Hill method the best. So, about 10 years after that, in 1941, the Huntington-Hill method was officially adopted as the method used for congressional apportionment in the United States. It is similar to Webster's method, except it uses the geometric mean, which I'll talk more about in a minute. It is also called the method of equal proportions. So, in general, the Huntington-Hill method calculates the standard divisor, and that is the ideal size for a congressional district in the United States. The goal of the Huntington-Hill method is to apportion representatives so that each state's average size for their congressional districts is as close to that standard divisor as possible. So let's take a look at some of the steps. Just like all the other methods, we start out by finding the standard divisor, which is the total population divided by the total number of seats, and then find the standard quota for each state. So we do the state population divided by the standard divisor. Now, here's where it gets different. You're going to take the lower quota, which remember is the standard quota rounded down, and the upper quota, which is the standard quota rounded up, and calculate the geometric mean of those two. Geometric mean is the square root of the product of two numbers. So in this case, we're going to have square root of the lower quota times the upper quota. When we looked at Webster's method, we rounded normally. So if your standard quota, the decimal part of your standard quota, was 0.5 or higher, you round up. If it was less than 0.5, you round down. Well, now, instead of using 0.5 as our cutoff for rounding, we're going to use the geometric mean. So if the standard quota is greater than the geometric mean, you round up. If the standard quota is less than the geometric mean, you round down. If the total apportionment is equal to the number of seats, then you're done. If not, then you need to modify your divisor until you have the correct number of seats apportioned. Now, I know that sounds like a lot, and this is the most mathematically complex model of the models that we've looked at. But if you use spreadsheets, again, I promise it's not that hard. So, we're going to look at the same example that we looked at with Jefferson, Adams, and Webster's methods. A small republic consisting of 6 states has 250 seats in Congress. Find the apportionment of the republic under the Huntington-Hill method. And we've got the population of each of the states. I'm going to flip over to my spreadsheet and do all of my work there. So, again, I have the states and their populations listed. I wrote a formula to add up all of the states' populations to get the total population of this small republic. We are told that they have 250 seats in Congress. Now I'm going to calculate the standard divisor. Remember, the standard divisor is the total population divided by the number of seats. So my standard divisor is 50,000. Now I'm going to calculate the standard quota for each of these states. Remember, to calculate the standard quota, you take the state's population and divide by the standard divisor. In the last video, I showed you a little spreadsheet trick. Since we are always dividing by the standard divisor, I'm going to put dollar signs in front of the B and in front of the 10 to lock that, so I will always divide by B10. Now I can go ahead and copy and paste this formula for the rest of the states. So that's my standard quota for each of those states. Now, to find the lower quota, I need to take the standard quota and round down. Remember, the function for rounding down is floor. So I'm going to type equals floor, parenthesis, click on my standard quota, and then I can copy that down for each of the states. For the upper quota, the function is ceiling. I want to take the standard quota and round up. So I'm going to type equals ceiling, parenthesis, and click on the standard quota. Then I can go ahead and copy that for the rest of the states. So far, the functions that I've used in this spreadsheet are ones that I've already shown you. Now, to calculate the geometric mean, we said we are going to take the lower quota and the upper quota, multiply them together, and then take the square root. So here's how we can do that in the spreadsheet. If we type equals SQRT, that's the abbreviation for square root, parenthesis, lower quota, times, which is shift 8, upper quota, parenthesis. So that will calculate the geometric mean of these two numbers. And then I can just copy that for each of the other states. Now, here's the tricky part. You could do this by hand, which is fine. I'll show you how to do it in the spreadsheet as well. So, when we decide how to round, we are going to compare our standard quota and our geometric mean. If the standard quota is larger than the geometric mean, which for state A it is, we round up. So we'd round this up to 33. So if you want to do that manually, compare the standard quota and the geometric mean and decide how to round, you can do that. There is also a way to do this with a formula, and it involves using an if statement. So, to use an if statement, you would type equals if, parenthesis. Then you need to come up with a logical statement that is either true or false. So I could say, if this number is greater than this number, that's my if statement. I'm going to put a comma. And then I need to ask myself, what happens if that statement is true? So if my standard quota is greater than my geometric mean, I need to round up. Well, rounding up is just the upper quota. So if standard quota is greater than the geometric mean, my answer should be the upper quota. And then I'm going to put another comma. And I need to say what to do if that statement is false. Well, if the standard quota is not greater than the geometric mean, then I want the lower quota. So this formula tells the spreadsheet if my standard quota is greater than the geometric mean, I'm going to use the upper quota. If not, I'm going to use the lower quota. And we can copy that for each state. So that's the basic idea. Now we need to check and see if we have given out the right number of seats. So I'm going to do equals sum and highlight those values. I have given out 251 seats. I only have 250. So now here's the familiar part. I need to adjust this divisor. Since I've given out too many seats, I need to make my divisor a little bit larger. So let's try 51,000. Now that was way too much, so let's go to 50,500. Now 50,100. Okay, now I have given out 250 seats. If you thought that these if statements here were a little too confusing and you just decided to round it yourself, you would need to double check the rounding after you adjust the divisor each time. So I'm going to go ahead, copy this information onto my slide, and then I'll come back and I want to look at one more thing. So now, this is our final apportionment using the Huntington Hill method. Originally, we had one extra seat, and if you look, it was actually our largest state that lost a seat when we adjusted the divisor. Now, there are a few issues with the Huntington Hill method. Montana actually sued the federal government in 1992 because they believed that the apportionment using the Huntington Hill method was unfair. In the apportionment following the 1990 census, Montana actually lost a seat in Congress. They went from having 2 representatives to only having 1. So, of course they wanted to find an issue with the method. And their argument had to do with this last column here. So I'm going to calculate population per representative. So each of the members of Congress, how many people do they represent? And to do that, all I have to do is take the state population and divide by the number of representatives they have. I'm going to copy that down. So, the goal of the Huntington Hill method is to pick a divisor. This divisor represents the ideal size of a congressional district. So, in this country, ideally, each representative in Congress would represent 50,100 people. So, all of these values you can see here are pretty close to 50,100 people. We've got 49,800 and some, 50,200, 51,000, 49,700 and some, 48,900 and some, and 49,400 and some. So Montana's argument was that if they had 2 representatives, instead of the 1 that they were given in 1990, that their population per representative would actually be closer to this ideal congressional district size. The case went to the Supreme Court. The Supreme Court decided that the Huntington Hill method is fair and Montana needed to stop complaining. Now, this method is more complex than the methods that we looked at previously. So it can be a bit confusing for the average citizen to figure out how on earth they decide how many representatives each state gets. And lastly, the Huntington Hill method slightly favors smaller states, and let me show you why. The Huntington Hill method uses the geometric mean as the cutoff for rounding, instead of 0.5, like normal rounding with Webster's method. So here, I have calculated the geometric mean for consecutive integers. So a state like Montana, who would be entitled to 1 point some number of representatives. If you're trying to decide how to round, instead of using 1.5 as the cutoff, you would actually use 1.41. And you can see, if you just look at the decimal part of each of these geometric means, you can see as the upper and lower quota increase that the decimal part gets closer to a cutoff of 0.5. So using the geometric mean actually makes it more likely that you round up than with normal rounding. And for small states, it's actually much more likely that you round up when you compare that to larger states. Because here, the cutoff, the decimal part, is 0.414, but when you're looking at states like California, California had 53 representatives after the 2010 census, the cutoff would be 0.497. So it slightly favors the smaller states. And that's our last method of apportionment that we're going to discuss this unit.